So here we're going to be testing the difference between sample means when we have dependent samples. A little bit different from the previous sections. We had assumed independent samples, but this is a case where you may ask the same person two questions. Ask them a question at one point in time and ask them a question at another point in time. That would be an example of dependent samples because they're paired. So what are the conditions we need? We need the samples to be randomly selected. The samples will be dependent paired samples. We also want the populations to be normally distributed, or the number of pairs be at least 30. So if these conditions are met, the sampling distribution d bar will be the mean of the differences that we get when subtracting the dependent sample entries. And we'll use a t-distribution for this approach with n minus 1 degrees of freedom, where n is the number of data pairs that we have. Alright, so n is going to be our number of data pairs. D is going to be the difference between entries. Mu with a subscript of d is the hypothesized mean of the differences. And then d bar will be the actual statistical mean of the differences that we get from our participants. S with a subscript of d will be the standard deviation of the differences between the paired data entries. Here's the steps for performing this kind of test. We want to verify that the samples are randomly selected, that the samples are dependent paired, and the populations are normally distributed, or n is at least 30. Let's check out an example problem here and see if we can follow along with the steps. So let's see. A shoe manufacturer claims that athletes can increase their vertical jump heights using the manufacturer's training shoes. The vertical jump heights of 8 randomly selected athletes are measured. After the athletes have used the shoes for 8 months, their vertical jump heights are measured again. The vertical jump heights in inches for each athlete are shown below in this table. We'll use an alpha level of 0.1. Is there enough evidence to support the manufacturer's claim? Assume the vertical jump heights are normally distributed. So, as you can see, we don't have an n that's at least 30. We only have 8 data pairs, so our n is 8. Let's write that in. Jump heights should be normally distributed. Some people jump really high, some jump not so high, but there would be some average height around which most people would jump, so it's conceivable that this, like many things in science, would be measured to be a bell curve. It is dependent samples because it's the same person doing the jumping. So all the conditions are met here for doing this type of test. Now we have to decide what claim is being made. Alright, so this shoe manufacturer claims, you always want to look for that word, claim, athletes can increase their vertical jump heights using the shoes. They're going to claim that the jump height after using the shoes is greater than the jump height prior to using the shoes. Now every difference is calculated like this. And so if they're equal, we'll get a 0 out of that. If there's no change, I mean, in the jump height after wearing the shoes versus before, we'll get a difference of 0. But what this manufacturer is claiming is that the difference would not be 0. Does the claim include equality? If yes, then HO is the claim. Write the null hypothesis and alternative hypothesis. That was already done for us in that problem. We want to write claim next to one of these and assume the null is true. We'll find the significance level and then determine if it's a left, right, or two-tailed test. Alright, so significance level is 0.1. This is a left-tailed test. So let's draw that in. We have to find the t that goes along with this. So just like before, we'll use a degree of freedom of n minus 1. It's going to be 7. So I'm going to go to the t table, look up a one-tailed test for an alpha of 0.1. Alright, let's look up the degrees of freedom of 7. Let's find one-tailed 0.1. So we're looking at 1.415. Okay, now what we have to do is we have to calculate each difference for every person who participated here. So we'll do, if we're doing initial minus final, then we expect that we would get a negative. Okay, and that means that this would actually be the claim. We will subtract straight across. So that means we'll do 24 minus 26 to get negative 2. 22 minus 25, negative 3. This will be 0, negative 1, 2, negative 2, negative 5, and negative 3. A lot of the evidence that looks good for the manufacturer, that's what they want. They want the before to be less than the after. Now, the formula that we're going to plug into for the differences is going to be this. We need the mean of the differences, and we also need standard deviation of them. So we could just plug into calculator. Alright, so we'll put in negative 2. Okay, there's all my differences. I'm going to hit stat, calc, one variable stats. Our mean comes out to negative 1.75. Alright, our standard deviation 2.12. Alright, now we will use the formula for the test statistic, which is going to be this right here. Similar to what we had done previously. Alright, so we're going to have negative 1.75 as our actual differences between the before and after. And we'll subtract a 0 because that's going to be the hypothesis here. And we'll put that over 2.12 over a square root of 8 because there were 8 participants. Alright, from this we'll decide if we're in the rejection region or not. Negative 2.33. So we are in the rejection region. Okay, we will reject HO. And that means we don't like this and we like the claim. So at the 0.1 significance level, there is enough evidence to support the claim that the shoes can improve jump height.